My name is Xin Yuan, and I'm from Pennsylvania State University. I'm appreciate this opportunity to share our work, learning locality-sensitive bucketing functions. Many tasks in sequence analysis need large-scale sequence comparison, such as constructing overlap graphs and multiple sequence alignment. They can be defined as identifying all pairs of similar sequence by their edit distance. But there's two challenges. The first is large-scale pairwise comparisons is difficult to imply because of it could be huge amount of computation. And the second is edit distance is not computable in subquadratic time. Locality-sensitive hashing function is a way to implying large-scale sequence comparison. So what is this locality-sensitive hash? First, please pay attention on the left or coordinate. It shows the sequence in the original space that the two nodes here, S and T, close to each other represent they are similar sequence with smaller edit distance. And R, which is far away from them, which represent the sequence not similar to them. And the locality-sensitive hashing functions, we also call it LSH functions, maps the sequences to a latent space, shows on the right side, which with high probability maps similar sequence to the same hash code, and this similar sequence to the distinct one. So LSH functions can quickly rule out the irrelevant pairs by only comparing sequence with the same hash code. However, designing a hash function that can accurately and sensitively map similar sequence into the same bucket is extremely difficult. Existing LSH functions only works when edit distance have a big gap. So in order to achieve a balance between the sensitivity and computation time, the previous work of our group proposed a locality-sensitive bucketing functions. They map a sequence to buckets of hash code rather than one. So more specific about this LSB functions, first let's define a D1, D2 sensitive LSB function. It maps sequence to k buckets of hash code, and if the sequence pair in the original space with an edit distance less or equal to D1, with high probability at least share one hash collision, for example, S and T. And if the sequence pair in the original space with an edit distance larger or equal to D2, with a high probability, there's no hash collision. So LSB functions are guaranteed to identify sequences with smaller edit distance while also avoiding comparing irrelevant pairs. But actually designing a LSB function is, for critical D1, D2 is challenging. The first is because designing a D1, D2 LSB functions manually is quite involving. And for some harder D1, D2 sensitive, the theoretical LSB functions need a huge number of buckets. So how to design an arbitrary D1, D2 LSB functions with optimal K? In our work, we're training LSB functions by a machine learning model. This page is we designed a learnable LSB functions, which is a neural network G followed by a rounding procedure. First, the neural network takes a length of sequence n as input and gets a k buckets of hash codes with m dimension. And then k buckets of hash codes are rounded to k binary vectors using threshold theta. Here is 0.5. Elements above theta will be 1 and otherwise 0. And this is the structure of the neural network G, which is an inception CN model, shows in this figure. With the input, the sequence length of n, models contains several inception CN layers, and the layers number based on the length of the input sequences. For each inception CN layer, it's composed of various sizes of kernels to capture the various shared substrings. And the output features of the last inception CN layer go through a flitting layers and will be sent to K buckets, which each containing an m-dimensional vector. More specific of this CN unit, here is an example of the building block for each CN max pooling unit. We train a convolutional kernel followed by a max pooling operations to capture shared substrings. And here, a shared convolutional kernel is a hashing function that gets the hash value of the former subsequence. And the max pooling picks the maximized hash values in the window, which here in this example is the hash collisions corresponding to the shared GACT. And we can see this training CN max pooling unit is like the work of the minimizer, but the better thing is that parameters of the hash functions can be optimized by training. So it is like an optimizable minimizer. So how to train this exception CN model? First, we have this training samples for LSB functions, which are pairwise sequences with length of n, and the output for the similar sequences -1, which are the sequence pair with the edit distance equal or smaller than d1, and for the non-dissimilar sequences with 1, which they are with the edit distance of larger or equal to d2. And for this pairwise input, we utilized a Siamese neural network with a pair of input that share the neural network with the same structure and parameters. A general hinge loss function is adapt, which is outperformance in binary classification. And in our work, we discussed 4 different loss functions, which was the 2 norm and the infinity norm with the directly inception CN procedure and the round inception CN procedure. Well, with training these 4 different loss functions, we find that first, the infinity norm is difficult to train compare with the 2 norm, and the rounding functions need to transform G into F is not differentiable. The comparison results show on the following page. And this page is our experimental setup. We simulated sequences pairs for lengths of 20 and 100 with various edit distance. And we discussed the parameters, including various D1, D2, the length of sequence N, and the bucket number K. And we compared with this following method, the variance of loss functions, the other machine learning models, and order mean hash. And we evaluate the model by the accuracy. It is a binary classifications, and the edit distance less or equal to, and the sequence pairs with the edit distance equal or less than D1 are positive samples, and with the edit distance larger or equal to D2 are negative samples. And this is the comparison of the 4 forms loss functions we mentioned before on the sequence length of 20. we tested the 4 loss functions L on 6 D1, D2 LSB functions, which are 1, 2, 1, 3, 2, 3, 2, 4, 3, 4, and 3, 5. And from this table, it can be seen that the Z4 consistently outperforms all these D1, D2 sensitive LSB functions. So we used the Z4, this one, as the loss function in the following experiment. And this page shows the validation set loss function of the 6 D1, D2 LSB functions we mentioned on the last page. And we discussed on 3 bucket numbers, which are k equal to 1, 10, and 20. And we can see that the curves of k equal to 1, which is this blue line, always converge to a higher range than the k equal to 10 or 20. And this also proves that the LSB functions, the LSH function mapped to 1 bucket can barely be trained compared with the LSB functions mapped to multiple hash codes. And this page is the accuracies of this 6 D1, D2 LSB functions testing set. And from this table, we can see that first is the accuracies of the 1, 2 LSB functions and 1, 3 are nearly perfect, which proves the power of our learning framework. And for the other LSB functions, we can see using k equal to 1 reduce accuracies significantly, again, attesting to the necessity of using multiple hash codes. And we also compared the LSB function on the 4 other new machine learning models, which the first one is a linear model with a 4-layer or fully connected neural network. LSTM models contains 2 layers of LSTM and a linear layer. And there's a CN1, which is a shallow model with 4 convolutional layers, and CN3 is the deeper one, contains 8 convolutional layers. And all these models are trained and tested with the same set of simulation data. We can see that both CN models with these 2 lines significantly outperforms than the linear and LSTM models. And our inception model further enhanced the CN models by capturing various lengths of substrings within inception layers. And we also compared with order-mean hash, which as the first and state-of-the-art direct LSH method for the edit distance. The figures shows the accuracy at each edit distance can be compared. But both methods works nearly perfect on this larger edit distance. But we can see that the trained LSB functions have significantly higher accuracy than order-mean hash for the edit distance below to D1. And the LSB functions can improve the LSB function can improve the sensitivities by capturing a large number of true matches that are potentially missed by order-mean hash. Well, in summary, this work established a learning framework to train arbitrary LSB functions. The performance of learnable LSB functions validates the machine learning framework's capabilities and reassures the effectiveness of LSB functions. And with the machine learning framework, training any LSB functions with the parameters of user's choice, including n, d1, d2, and k, can be easily achieved. And for future works, since the pairs with an edit distance near D1, D2 are more likely to be hashed incorrectly in some of these LSB functions, we want to improve the performance of the sequences on this edit distance near D1, D2. And there's a limitation of our current work is that the Siamese neural networks requires the sequences to be the same length. So we want to extend our method to sequences comparison without the limitation of same length. And the full paper and the code of LSB functions available at the following link. And at last, I want to thank my advisor, Ming-Fu Xiao, and the funding support and all the members of our group. And thank you for your attention. I'm ready for questions.
So are there any questions? Yes, we have one.
Hi, thank you for the talk. There are some pairwise sequencing in alignment algorithms that run in time ND instead of just being N squared. So I was wondering if you guys had a chance to compare, let's say, your optimized LSH functions to some of those algorithms, like especially at lower edit distances.
Lower, sorry, repeat your questions.
Okay, so yes, a lot of pairwise sequence alignment algorithms run in N squared time, but there are a few that actually run in time ND, so N multiplied by the edit distance. So since you were focusing on, let's say, LSHs that are targeting smaller edit distances, I was wondering if you had a chance to compare how long your optimized LSH runs compared to some of these other alignment algorithms. Like I mean, just comparing how long it takes to let's say compute
time of computing compare with the LSH functions.
Exactly. Yeah. Like how long does it take to do the comparisons?
Yeah, actually, yeah, there's some results about this running times in our papers, but because of the time I didn't show in these presentations. Yeah, actually, we are much faster than the LSH functions one of like they took for the same data set, when they took about 100 seconds, we use only 10 seconds. So we are much faster.
Okay, I'll take a look through the paper then. Thank you.
Thank you for your question.
Any other questions? Maybe I would ask, so there is a lot of like theoretical research on Hamming distance. Do you think your functions would be very different if you used Hamming distance instead of edit distance?
Yeah, it is like edit distance is more useful for this detecting the similar sequences. Yeah, of course, there's some way like using Hamming distance or other distance, but so it is like it's hard to imply this edit distance. So we need this algorithm. But if using Hamming distance, like it can be simple, but some questions cannot be solved. I think that's the necessity of using edit distance. Yeah.
Okay, thank you.